Let's talk about estimating the regression coefficients. So remember when we're doing simple linear regression that it turns out, when you're talking about one response variable based on one predictor variable, y equals b naught plus b1 times x, it turns out that the slope coefficient equals r times sy over sx. And b naught, your intercept coefficient, turns out to be y bar minus b1 x bar, right? Okay, well it turns out that it's real simple, even in this very general context, even when you can possibly have polynomial models and so forth. That there's a real. Here's the punchline. Show it to you right here. This is how you write down your vector of coefficients of your coefficient estimates of your model for your model parameters. And here's how you can see this. Let's let Q, just because we need some symbol for it, be the sum of squared errors. Okay, that is, if you take all your response values, subtract off the fits, okay, and square those and sum them up. This is your sum of squared errors. Then I can write this as the sum of squared. Let's see, yi comes down. I'm just gonna plop in my y hat I, what I'm letting with these hat values, the hatted y's are, yi hat is beta naught plus beta 1 xi1 plus, oops, missing a subscript there, should be a 2, I guess. I'm just dropping in my expression for yi hat, and let's see, I'm going to let b be our vector of estimates for the betas. So it's, b naught is beta 1 hat, b1 is the same as beta 1 hat, that's b naught is beta naught hat, sorry. So let's write down then, using matrix notation, what's our vector of our sum of squared errors. It's not a vector, it's just a sum of squared errors. I can write this in vector or matrix notation as, well, let's see, if I look at if I just look at what is y minus x beta, x times beta, this is my these are my y hats, right? So y minus this stuff is a vector of errors, right? And so if I take this vector, if I think of this as a column vector and I take its transpose, then it's a row vector. So this is how I get a sum of squares, right? If I have a vector of a bunch of numbers and I want to square those numbers and then sum them all up, I just take the transpose of it and then dot it with itself like that, right? Okay, and so I can rewrite this as y transpose minus beta transpose x transpose, right? You should play with that. Make sure that you understand that. If you take if I take the transpose of a sum or difference, but if I take the transpose of a sum of matrices, it's the sum of the transposes. And so then in here I would have y transpose minus the transpose of all of this stuff. Now remember, the transpose of the product is, you have to it's the product of the transposes, but you have to interchange the order in which you multiply. This is basic matrix stuff, right? Okay, so now I have this stuff times this stuff. Now I'm just going to FOIL, right? This is y transpose y minus beta transpose x transpose y, and then minus, I've got a y transpose times x beta, plus, finally I've got all this times all this, so it's minus is a plus, and I've got beta transpose x transpose times x times beta. Okay, I've got all this stuff. So then all this stuff is equal to y transpose y. Now it turns out that you can actually combine these two terms, and I should ask you to answer why it's okay to combine these two terms to get 2 beta transpose x transpose y. How can you combine these two that way? I'll let you think about that. Plus, finally, all this same stuff over here. Okay, so now, how did we, what's our next move? Remember, you want to, the idea is you want to minimize this sum of squared errors. So I want to differentiate Q with respect to each one of those betas, right? And set each one of those derivatives equal to 0. Hopefully it'll be convex in the in these betas. So when I do that, if you differentiate with respect to beta, what do you get? All this stuff goes away, right? And you'll have -2, and then you're just left with this stuff here, okay, for this term. And again, differentiating with respect to the beta. So now this stuff, you want to think of this is like a quadratic form, right? This is a variable, this is a variable, and then there's some stuff in between. Sort of like this stuff times beta squared, right? Sort of. So it turns out when you differentiate this stuff, one of those betas goes away, and you just get 2 times, because the exponent comes down, right? If this is sort of like beta squared times this stuff, you'll get a 2 times this stuff times beta. Okay, so there's we sort of ran over some matrix multiplication stuff there. Hopefully, if some of that stuff you're a little fuzzy on, then maybe you want to review it. But this is our this is the derivative of this is our vector of derivatives. This is our vector of derivatives of the sum of squared errors with respect to each one of our betas. Okay, so now if I want to set each one of these guys equal to 0, so set this equal to the 0 vector, then that means that this term equals negative this term, or this term equals negative that term, or whatever, right? And the 2's go away, and you get x transpose y equals x transpose x b. Now, so if you can, I guess if you can take the inverse of this matrix, this is where it boils down to. If you can invert x transpose x, then you get B equals x transpose x inverse times x transpose times y. Okay, so this matrix multiplication step in here will give you your least squares coefficient estimates. Okay, so this is really important. You definitely need to memorize this or get it tattooed on your hand or something. If you're a statistics student, you need to learn this for sure. Say it about 100 times over and over. So I'll let you think about this stuff, but of course the evaluation of this depends on whether or not this x transpose x is actually invertible. If the columns of x are linearly dependent, then the parameter estimates will not be unique, and we can run into some problems there, which we'll address some of this later on when we talk about multi-collinearity and also when we talk about principal components. There are some other methods too, some things, some automated methods called things like steepest descent methods for using a computer to approximate the coefficients if this matrix is if the matrix is too large, it could take a ton of time to try to invert. So, but for the most part, for what we do, this we won't have a problem. Okay, and this x transpose x matrix will be invertible. Okay, so I've got R pulled up here, and at this point, I'm going to open up that Toluca data set. Again from chapter 1, that's that ch01ta01.txt file from your Kuttner data values and data sets. Sorry, if I take a look at this data, you'll remember it's we've got lot sizes here and work hours over here, and I guess we want to try to predict work hours based on the lot size, right? So so here's what I'm going to do. I'm going to do this quote-unquote long way using matrix multiplication, and then I'm going to use R to do it the really quick way. So first of all, I want to get a vector of ones, right? Here's a quick thing, by the way, rep for repeat, I guess. If I want to go like say 1 to 20 and I want three of those, this will just do You know, what does that look like? 1 to 20 three times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 20, and then repeat it. 1 through 20, 1 through 20. Okay, that's not actually what I want, but it's something to for you to know how to do. I actually want to go from 1 to 1 and do this, gosh, how many times? However many rows are in my data set. That's what I want, because I want that column of ones to include into my data matrix X, right? So X is going to be, I'm going to column bind the ones with the first row in that Toluca data set, or sorry, the first column in the Toluca data set. So now if I look at head of X, I'll see that I've got my ones there and then my X variable values right there. Okay. So now my I can get my least squares coefficients. By the way, the R command for finding the inverse of a matrix is solve. Okay, so I want to find. Remember the function, or the expression here is that B, my vector of coefficients, equals X transpose X quantity inverse times X transpose times Y. X transpose X quantity inverse times X transpose times Y. All right, so I'm taking the inverse here. I've got X transpose, right? That's the transpose of X, times X, and then I'm taking all of this right here is going to be the inverse of X, and then I want to say times the transpose of X times Y, where actually Y is the second column in my data set, I guess, right? Okay, there we go. So now if I just take a look at B, there we go. Here is my my intercept coefficient, and here's my slope. And I can check that if I do out linear model, data, second column versus data first column, like so, and take a look at the summary. Yep, there it is. Okay, there we go. They're the same. Very nice, huh?